Okay, so what I want to do today, this is Math 383 Complex Analysis, Lecture 22, is I want to talk a little bit about recurrence relations, especially for sums, and talk a little bit about how you would solve in some special cases, or how you would, if you can't solve, at least approximate the answer. And depending on what techniques you have, you can get different levels of approximation. And so the main ideas are attacking special cases. It's often easier to understand a special case first and then build from that to the general case. Another time is you start off with a simple problem, which you can solve completely, and then you perturb it. So solve the simple case and then make it more and more complex and try to handle the complexity as it comes in a little bit at a time. If you cannot solve the simple special case, odds are unlikely you will be able to solve the general case. It may be, unfortunately, the case that if you try to look at something that's too simple, you might try to be looking at it the wrong way. You might be focusing on maybe some special properties that have absolutely nothing to do. One of my favorites is that, who knows what theorem I'm thinking about? Yes. At least one of these is transcendental. We actually believe that it's both, but it's very easy to prove that at least one of them is transcendental. If you've never seen the proof before, what do you think might play a role in the proof? Given that this is a complex analysis class and we're talking about E and pi, what do you think might play a role? Which complex numbers, which relation? Yes. E to the I pi equals -1. This absolutely has nothing to do with that. It's a statement about the sum or the product of two transcendental numbers. At least one is transcendental. But if you look at the very special case, you might try to focus on specific properties of them rather than stepping back and abstracting. So just something to be aware of. And then the last is we're going to do a lot about dyadic decompositions, breaking something up into two smaller subproblems and then breaking those up and breaking those up. If you've done computer science, this should sound very familiar. And then trying to just piece all of this together. So I'm not going to go through, we've already sketched a proof of the prime number theorem earlier when we did contra integration. There's other arguments you can make to estimate why this should be right. Rather than doing that, it's in the book. I'm also going to just post the slides from that lecture. I want to spend today talking about things that often fall through the cracks. And these are things you should have seen. These are very useful techniques. And I want to just discuss how you would solve problems like this. So we'll first start off with Stirling's formula. So, in I think the previous lecture we talked about the gamma function, gamma of s is the integral of e to the negative x, x to the s minus 1 dx. We talked about why we wanted to write it as x to the s minus 1. This gives us, dx over x with x to the s. This is why we're doing it that way. And we had that gamma of n plus 1 is n factorial if n is equal to 0, 1, 2, ... So this is a generalization of the factorial function. And Stirling's formula, which is exceptionally useful, is that for large n, n factorial is approximately n to the n e to the minus n squared of 2 pi n. Now, there's many reasons why this is beautiful. It combines two of the constants we truly love, e and pi. We're having the Cauchy-Riemann battle this semester. You could have a battle between e and pi. Maybe we could convince Garrity and Adams to do a debate on that. They haven't already done so. This uses both. When you see a square root of 2 pi, what do you think of? Standard normal. So there could be a normal lurking somewhere in here. And we showed that the gamma function is related to the to the moments of the normal distribution. So maybe it's not so surprising that there's a square root of 2 pi coming in. So if you've never seen proof of Stirling's formula before, this actually gives us a little bit of a clue as to how to attack it. And we will give a rough proof of this later using the method of stationary phase. This is sometimes done in physics classes as well. Extremely powerful technique. The idea is it's often hard to study something that's discrete because what can't you really use for something that's discrete? You've taken a bunch of classes in this. Yes. Calculus, right? All calculus is gone if things are discrete. So what we do is we smear it out, we make it continuous, we analyze it, and then we specialize at the end of the day to the integers. So again, very powerful technique. And so more precisely, we can actually have a convergence, we have a series expansion where depending on where you truncate, the terms are getting smaller and smaller and smaller, and you can decide what level of approximation do you really want. Now, if you think about on an absolute scale, the first lower order term is of size 1 over 12n. It's being multiplied by something that's incredibly large. So on an absolute scale, the lower order term is quite large, but it is small relative to the main term. How small? Well, roughly 1 over 12n times the main term. So we have to be very careful always when we talk about what size of things. Frequently, this is telling us we're looking at the wrong thing if we study n factorial. What might be better to study than n factorial? Well, the given function is essentially n factorial, so yeah, but instead of studying n factorial, what should you study? The log of n factorial, right? You should have a Pavlovian response anytime you see a product, right? You want a candy bar? Oh, sorry, I was trying to make sure that it didn't go to anybody around you, so I had to have it high and to the right. I apologize. Right? Whenever you see a product, you should be thinking logarithms. If we do a log, all right, well, then the main stuff over here is going to be a nice main term, then we'll have the log of 1 plus something small. And so this tells us maybe the log is a better thing to study. So the first thing is, can we get some crude upper and lower bounds? So we're studying n factorial. I will accept really crappy, shitty bounds. And I have to put in the trigger warning. All right. Can somebody give me a really bad either upper or lower bound for n factorial? Yes. Yes, it is definitely less than or equal to n to the n. And how about a lower bound? 0. And yeah, so 0, 1, less than or equal to n, less than or equal to n factorial. Any of those would be fine lower bounds. At least a little bit better than 0, but 0 is still an acceptable lower bound. Why, in some sense, is a 1 a better lower bound than n? Well, we're taking the absolute smallest number and we're repeating it every single time. N is just saying, well, look, let's just look at the product and just take the largest element of the product and just use that. Whenever you see a formula, you always want to check and see, is this reasonable? Well, we know n plus 1 factorial over n factorial is just n plus 1. So we can see, is Stirling reasonable? So let's try approximating n factorial is about n to the n, e to the minus n square root of 2 pi n. N plus 1 factorial would be approximately n plus 1 to the n plus 1, e to the negative n plus 1, square root of 2 pi n plus 1. And so if we look at n plus 1 factorial over n factorial, that's approximately n plus 1 to the n plus 1 over n to the n. Then we have an e to the negative n plus 1 divided by e to the negative n. All right, e to the negative n minus 1 over e to the negative n. Then we'll have a square root of 2 pi n plus 1 over square root of 2 pi n. So what do we get? Well, we have n plus 1 to the n plus 1 over n plus 1. Let me write this. We have an extra n plus 1, so let me just pull that out. And now we'll have an n plus 1 to the n over n to the n. Oh, that's just 1 plus 1 over n to the n. Then the next one is going to be a 1 over e, or e to the minus 1. And then we have the square root of 2 pi's cancel. We have an n plus 1 over n, so we'll get a square root of 1 plus 1 over n. And as n gets very, very large, the 1 plus 1 over n to the n converges to e. So this is like e times 1 over e. So this, yeah, it really does look like it's approximately n plus 1. So again, this is not a proof of Stirling's formula, but it's at least consistent that it does look like it's growing at the right speed. Okay, so you should have seen Stirling's formula when you did something similar to Calc BC or multivariable calculus, when we're trying to figure out which functions converge. N factorial just has such rapid growth that we can prove basically the series expansion for the exponential converges, and it converges absolutely. And so you just use this thing to show that it's going to grow faster. So no matter what, the numerators are growing only growing only polynomially. So every time we add another term, we increase the numerator by a factor of x, but the denominators are increasing by a factor of n. So this is going to be a comparison with geometric series. So comparison with geometric series. So you should go through and you should make sure that you are able to prove that the exponential function converges to any input. And again, it's just going to be a really nice comparison. From some point onward, you'll have a ratio that's going to be less than a half. Okay. So how many of you remember the integral test from calculus? How many of you do not remember the integral test from calculus? How many of you are kind of asleep right now? But not so asleep that you don't answer the question. Okay, all right. So one of the great results we have in calculus is to determine whether or not a sum converges or diverges and roughly how quickly it grows. If the sum is monotonic, we can basically replace it with an integral and control the error. So for instance, if we take the function n factorial, this is a product, we do have Pavlovian response, we take the log, and instead of studying n factorial, we study the log of n factorial, which is a sum. Oh, it's log of 1 plus log of 2, dot, 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 plus log of n. That's approximately an integral. And then because the function is monotonically increasing, what I can do is I can get upper or lower bounds by comparing it to the curve log of t. And so what the two curves here are is the upper and the lower bounds. So for the first one, what it's going to do is it's going to give me a upper bound by finding the area under the curve, because what I'm doing is for each of my pieces, I'm calculating the area going to the right. So for the log of 1, I'm going from like 1 to 2, for the log of 4, I'm going from 4 to 5. So it's always going to be a little bit less. For the other one, I'm going to the left. And so for the log of 1, I'm just pushing it to the other side. And so I have control over overestimating or underestimating. I'm sorry? So this is 2 units, 2 units. So this is going down to 1. So it's going down to 1 over here. And so you can see for the second one on the right, because I'm putting my box going to the left, the area under the curve is going to be a little bit less. And for the one on the left, it's going to be a little bit greater. And so I can sandwich the value of the sum of the log of k between the two. And one of the things you have to just unfortunately be a little bit careful about is, sadly, what are your bounds of integration? For the one on the left, I'm going from 1 to n. For the one on the right, I'm going from 2 to n plus 1. Not a huge deal. What's really nice about this is you can come up with really good formulas to control how much your error is. And it's basically going to be related to the first and the last piece, because you can see how much you're missing by between them. So you can make this extremely precise. I'm not going to go through all the details. It turns out that it's not that bad to find the antiderivative of log of t. And again, we need to find the antiderivative of log of t because that's what we're integrating. What function has the derivative of log of t? Well, this is just the method of divine inspiration. Try t log t minus t, and you see that it works. Why is this a good thing to try? Well, I want a function whose derivative is log t. So if I do t log t and I do the product rule, the derivative of t is 1, so I get 1 times log of t. That's great. But then I also have plus of 1 times the derivative of log of t, which is t times 1 over t, which is 1. Okay, so my derivative is almost log of t. If I just guess t log t, I'm off by 1. So I need to subtract a function whose derivative is 1. What function has derivative 1? That's t. So it's a fun exercise. You could try to figure out, is there a nice formula for the antiderivative of log squared t, or log cubed t, or log t to the nth power? And so first, we just go through, do a little bit of analysis, put everything in, and you get a lower bound of n to the n, e to the minus n times e. That's not bad. When you look at what we get from this, the upper bound, we differ by a factor of n. So the upper and the lower bounds, they're not the same order of magnitude. So that's a little bit bad. Let's put things in perspective. Okay? Really not order of magnitude similar. Here we're comparing n and n to the n. Not even close, right? But what do we have over here? We basically have 1 versus n. Okay, yeah, 1 versus n is large, but when you compare that to n to the n over e to the minus n, well, what is n to the n e to the minus n? That's just n over e to the nth power. N over e to the nth power is huge relative to n. If I gave you these two bounds, how would you average those two bounds to get what you think maybe the truth is for the value of n factorial? So they both have an n to the n e to the minus n, and they both have an e. So you have a 1 versus an n. How would you average those? Take the geometric mean, right? Why wouldn't you take the arithmetic mean? It works better, right? Well, what's going on in this problem? When we're doing something like n factorial, this is multiplicative. So that could be a good justification for using the geometric mean. If we take the geometric mean of 1 and n, it's just the square root of their product, which is the square root of n. So the geometric mean is just the square root of the product. The arithmetic mean is the sum of the two. And so there's a whole slew of different means you can use. Most of the time we use the arithmetic mean. The geometric mean is actually better for a lot of calculations. If you have a 1 on your first exam and 100 on your second, what is your arithmetic average, roughly? 50. What's your geometric average? 10. All right. So if we're talking about scores, for something like that, you want the arithmetic mean. What kind of assumption, or I'm sorry, what kind of conjecture might you make about the arithmetic mean and the geometric mean? Why? Yeah, the arithmetic mean is going to be larger. So your first conjecture is the arithmetic mean is always larger than the geometric mean. And it turns out that the arithmetic and the geometric mean are two extremes. If you have n numbers, you can multiply them all and take the nth root, or you can add them and divide by n. You could also look at all subsets of size k and get the k-mean. And you will have a whole family of inequalities going from the arithmetic mean at the largest to the geometric mean at the smallest. And so here, if we just do a little calculation like this, it suggests that maybe up to some constant, the answer should be n to the n e to the minus n square root of n. Again, not a proof, but it's really nice to be able to just quickly look at this and get some intuition of what we think the answer might be. And that's what I'm really trying to push today. All right, so I am not going to really go into the Euler-Maclaurin formula. Whenever you have Euler's name on it, it's a good rule of thumb, it's worth knowing. So I'm just putting this here as a placeholder, as a flag, that there are formulas that we have to find sums where you replace sums with integrals. Not surprisingly, the more smoothness you have, the more derivatives you have of your function, the better results you can get for the final sum in terms of your estimates. And so it's just worth knowing that something like this exists. How many people have never seen how to solve a recurrence relation for things like the Fibonacci's? All right, so I will just do this very quickly. So we want to solve recurrence relations. Say we have an plus 1 equals an plus an minus 1. Once I give you the two initial conditions, then everything is uniquely determined. Because once I know A0 and A1, then A2 is forced. And once I know A1 and A2, A3 is forced. I am not writing what A0 and A1 are because I have some people here who have done research with me on Fibonacci numbers. And depending on what problem you're doing, you either want to start the sequence 0, 1, 1, 2, or want to start it as 1, 2, 3. And that's why I'm not giving the initial conditions. So the best way to solve recurrence relations is the method of divine inspiration, where you basically, scratch your chin, point your finger to God, towards the heavens, whatever, and you write down the answer. And then you just show that the answer is correct. So let's guess that the answer is r to the n. This is a reasonable thing to guess because we know an plus 1 is less than equal to 2an, and it's going to be greater than equal to 2an minus 1. So what this is telling us is that an is growing slower than doubling. Every time you increase n, you know more than double. And every time you decrease n by 2, by the index by 2, you go down by a half. So essentially, every time you decrease the index by 1, how much do you go down by? Less than, well, how much? Doing it twice moves you down by a factor of 2. So if you move down the index down by 1, which do you move it down by? Square root of 2. So we might guess, up to constants, maybe root 2 to the n is less than equal to an is less than equal to 2 to the n. And just doing a quick thought experiment like this, a quick check, suggests, hey, maybe these ans are growing geometrically. And so let's try writing an as r to the n. This is a lot of fun to say as a Bostonian. Why do you think we use the letter r? Not ratio. Well, it's not bad. I think we use it for the word root. When we plug in an equals r to the n into the recurrence relation, this is called the characteristic polynomial. When we get r to the n plus 1 is r to the n plus r to the n minus 1. So we can remove an r to the n minus 1 because that extra factor of r to the n minus 1 just gives you as a solution r equals 0. Okay, well, yes, I could define an to be 0 to the n, and that will solve this equation, but it's going to be a really boring solution. And then you get r squared equals r plus 1, or r squared minus r minus 1 equals 0. The roots are 1 plus minus root 5 over 2. And then what you notice is that if you have a solution, if I multiply a solution by 5 or 7 or 13 by any constant, it's still a solution. And if I take two solutions and I add them, it's still a solution. So the general solution is going to be any linear combination of the two roots to the nth power. And then if you just choose appropriately, this is in the special case when a0 is 0 and a1 is 1, then you get one of my favorite formulas in all of mathematics, Benay's formula. And the way I like to explain this is, imagine that you're minding your own business and a Fibonacci number beats you up, all right? And they get a police lineup and you're trying to determine which number did this to you. Does this look like an integer? No. Everything cancels perfectly and it's an integer. A nice question is, what can you replace 5 by and 2 by? Because you've got divisions, you've got square roots. What can you replace those by and still keep it as an integer for every n? Beautiful, beautiful formula. It means you can jump and calculate the nth Fibonacci number without calculating all the stuff in between. How many people have ever done the Project Euler problems? So almost surely, somewhere I think in the first 10 is using something like this. It's been a while since I've done it, but I think it's in the first 10 where you have to use Benay's formula to calculate something quickly. You don't have to calculate every intermediate. You can just jump to where you want. We are fortunate here that we have two solutions, R1 and R2, that are distinct. If there's repeated roots, you have to do a little bit more work to find the general solution. Wonderful, wonderful theory. All right. So this is a sum everybody should have seen before. What is the most famous story that's told about this sum? This is Gauss. So what is the Gauss story? Okay, the version I've heard is he was 5. And again, I'm not sure, there's so many different versions. And the teacher was just having a bad day and wanted to shut up the little brats and told them, add up all the numbers from 1 to 100, thinking that this would give them, some time. And then Gauss just blurts out 50-50, 5,050. How did Gauss prove this so quickly? Yes, but what method did Gauss use?
Do it in pairs.
Do it in pairs. So you flip them and you write them backwards. And when you do it like this, you get n plus 1, n plus 1. And this is equal to 2 times the initial sum. So the sum is just n times n plus 1 over 2. Beautiful method. Unfortunately, it only works for the sum to the first power. It doesn't work if you try to do the sums of the squares or the cubes. All right, can somebody give me a formula to estimate this sum? Can you give me any estimates for Sn, an upper value or a lower value? Good. The most n squared. Your lower value? N. Okay. So it's not horrible, but you haven't given me the order of magnitude. Now, given that we know that the answer is n plus 1 over 2, we know which of these bounds is better, right? So if we had to fix one of these bounds, which bound do you think is more important to fix? N. So can somebody give me a better lower bound than n? Okay, why n squared over 2? Okay, so you're trying to, so here is basically, is n over here, n minus 1, all the way up to 1. And you're basically saying this is like half the total number of points. You have to be a little bit careful with the diagonal. But so as long as you're careful with the diagonal, you can make this work. And this will give you something on the order of n squared over 2. There's an easier argument to get a lower order that's of size n squared.
N squared over 4.
N squared over 4.
Half the elements about it.
Right. So what we do is, look at n over 2 plus n over 2 plus 1 plus n. And all of this is we have n over 2 terms. Each is n over 2. So with very little work, we actually get that it's somewhere between n squared over 4 and n squared. And so now we at least have the right order of magnitude. What if you take the geometric mean of 1/4 and 1? What do you get? So it's the square root of 1/4 times 1, which is 1/2, which is the correct leading term. But of course, if I had done your triangle, I had done an n squared over 2, and then tried that, I would not get the right thing over that. So you've got to be very careful. This is, where as a professor, I can often manipulate things in terms of being a little bit misleading if I so desire. But what I like about this is without actually solving the problem, we can very easily get that it's of order n squared, and the content is not really differing by that much. It's differing by a factor of 4. With a little bit more work, we can get it even closer. All right. So what I want to do now is I want to talk about lots of different ways of trying to prove this. And these will be useful techniques in analyzing a lot of sums that arise in number theory. And so if you haven't seen these methods before, these are good ones. What is the standard way that you were taught to prove stuff like this, especially if I replace the first powers with the second powers or third powers? Induction. Now, the problem with induction is you really need to know what you're inducting against, right? One way you could try to do this is the Online Encyclopedia of Integer Sequences, the OEIS. And if you just put in the first couple of values and you go to the OEIS, it will then tell you so much about the sequence. It might even give you the proof, it'll give you references, it'll give you proposed formulas. And so you could try to do it that way. So one way is to actually gather data is to be experimentalists. Sometimes you can try to do some special cases. Over here, when I did the argument here, was anybody bothered by anything when I was doing my lower bound estimate? When I said I have n over 2 terms, each one is at least n over 2. You don't know n is even. I'm making some comments about the triangle that you're giving us, or you got to be careful about the diagonal. And I'm just going warp speed and not even bothering to consider that n might not be even. So you have to worry a little bit about stuff like that. What is shampoo mathematics? Lather, rinse, repeat. Once we have an idea or method that's working, let's keep iterating and applying it again and again. So this idea of being able to break things up, what would be potentially the best choice of n to apply the shampoo method to? Yes, 2 to the n. So let's try to analyze where n is a power of 2 and see if we can figure out what's going on. And there's a lot of times when you can do tricks with evens and odds. So let's let an be 1 plus 2 all the way up to 2 to the n. Okay? And we're going to try to figure out what is an equal to. So again, this is not going to be a complete solution to the problem. It's only going to be a solution to the problem in the special case when n is a power of 2. So let me just remind you of a beautiful formula. What is zeta of 2 equal to? Pi squared over 6, which is the sum, n goes from 1 to infinity, of 1 over n squared. Now this is the same as the sum n is even of 1 over n squared, plus the sum n is odd of 1 over n squared. But what is the sum of n even of 1 over n squared? 1/4 of the whole sum, right? If you write n as 2 times m, with a little bit of thought, this is the same as m goes from 1 to infinity, 1 over 2m squared, plus the sum of n odd, 1 over n squared. So this is just 1/4 of pi squared over 6, plus the sum of n odd, 1 over n squared. So that means we can actually figure out the sum over the odds of 1 over n squared just from knowing the sum over everything. Can we figure out the sum over the evens? Yeah, that's actually even easier. So frequently, there is a nice way to pass back and forth between just knowing things over the odds and the evens. So we have our an is the following. So an plus 1 is going to be what? It's going to be 1 plus 2 plus 2 to the n plus 2 to the n plus 1 all the way up to 2 to the n plus 1. Yes? I can write this as the evens plus the odds. Right? Well, if you look at the sum of the even terms, how would you relate the sum of the even terms to an? I don't think so. Yes. It's just twice an. Because if I look over here for the evens, I have 2 plus 4 plus
an minus 1 or an plus. Okay, yeah.
So I have 2 plus 4 plus 6 plus 8. So if I pull out a 2 from everything, I just get the sequence an. Does everyone agree that the evens are just going to give me twice an? Yeah, the 2, the 4, the 6, the 8. So here, evens is equal to 2 plus 4 plus 6 plus 8 plus dot dot dot. And then the odds are equal to what? So what are the odd numbers? This is a prerequisite for the class. What are the odd numbers? Yes, thank you. 1, 3, 5, 7. So does anyone know what the sum of the odds would be?
It is going to be 7
Yes.
minus number of.
Good. I can write the odds as 2 minus 1 plus 4 minus 1 plus 6 minus 1 plus dot dot dot. So it's going to just be the evens minus n. But actually here n, the number of terms is going to be actually 2 to the n. So we have 2 to the n terms. Right? So I'm going to just get plus the evens, which is going to be another 2an, minus 2 to the n. So we get an plus 1 is 4an minus 2 to the n. Okay. Any questions on how we got this formula? Can we solve this? What would make this much easier to solve? What is related to this that would be very easy to solve? Can you give me a related recurrence? If that's the goal today. Start with something simple and perturb it. So can you give me a related recurrence that I can solve easily? Yes. Yeah. So try bn plus 1 equals 4bn. Okay, so the solution is bn is going to be 4 to the n times b0. Right? Yes, we just, every time we increase the index by 1, we multiply by 4. So we just need to know what the value of b0 is. So let's try to write an as, bn plus something. So the question is, what should we do that something as? Well, we know we have a minus 2 to the n. So let's try maybe alpha times 2 to the n. So an plus 1 would be bn plus 1 plus alpha 2 to the n plus 1. And I claim this is a really natural thing to try because I need to somehow deal with this 2 to the n. If I add a little bit on both sides, it's not the same factor. I have a 1 and a 4. So there's a chance of doing this and not having everything canceled. Did we do the bring it over method with integration when we had an integral and then the goal was to get it on both sides, but not with the constant 1 on both sides? Because if it's a constant 1, then it cancels. But if it's not a constant 1, then I can actually bring it over and cancel. So this is basically a child of bring it over. And so now if I try putting that in, I would get bn plus 1 plus alpha 2 to the n plus 1 equals equals 4bn plus 4 alpha 2 to the n plus 1 minus 2 to the n. So we have the freedom of choosing alpha. Let's try to choose alpha so that everything vanishes and we're only left with the b's. So we have 2 alpha times 2 to the n equals 4 alpha minus 1 times 2 to the n. Wait a minute. I think that should be a 2 to the n, not 2 to the n plus 1. Right? Do you agree? So what do I need alpha to equal? I want 2 alpha to equal 4 alpha minus 1. So 2 alpha equals 4 alpha minus 1. So 1 equals 2 alpha. So alpha equals 1/2. So if I take alpha equals 1/2, then I'm left with just bn plus 1 equals 4bn. Oh, that's what we want. So we then get an is equal to 4 to the n equals 4 to the n b0 plus 1/2 2 to the n. So all we have to do is figure out what is b0. So if I take n equals 0, what does a0 equal? So if I take n equals 0, what does a0 equal? An is 1 plus 2 plus dot, 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 plus 2 to the n. Yes. So a0 equals 1. So what does that make b0 equal to? a0 equals 1 implies b0 equals 1/2, implies an is equal to, we'll have 1/2 2 to the n plus 4 to the n. And let me just take a piece of, we got, an is 1 plus 2 plus dot, 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 plus 2 to the n is equal to 1/2 2 to the n plus 4 to the n. What can I factor out of 2 to the n plus 4 to the n? 2 to the n. So I get 1/2 2 to the n, 2 to the n plus 1. That's the answer. We just proved the answer. In the very special case when n is the power of 2, but we actually proved the formula. Unfortunately, this proof fundamentally uses the fact that we're looking at powers of 2. But this is a really powerful technique. And again, what we're really doing is we're perturbing an equation. So we're perturbing, Bn plus 1 equals 4Bn. This is a very easy recurrence to solve. And so we pollute it a little bit, we perturb it, we add in a little extra term. All right, let's look at another way to try to solve this. So we know that an plus 1, so now an is just going to be 1 plus 2 plus n. All right, so I'm no longer going to do powers of n, I'm going to just do the sum from 1 to n. We know an plus 1 is equal to an plus n plus 1. Right? If I didn't have the n plus 1, would this be an easy equation to solve? Right? So what would be the clean equation? Would be Bn plus 1 equals Bn. This is not hard to solve. Right? What's the solution? B0, yeah, just whatever that initial constant is. So what I want to do is I want to figure out what should I perturb by. So I want to try an, it's going to be my Bn, which is nice. And now I have to put something in. What do you think I should try to put in? Well, I need to put in something so that when I put it in for an plus 1 and an, it's going to cancel the n plus 1. So what kind of term do you think I'm going to put in? Do you think it's going to be a constant, a trigonometric, an exponential? It's going to be what? So one possibility is to try linear. And if you try linear, it turns out it's not going to work. So you're sad. And now what do you do once you find out that linear doesn't work? Try quadratic. So let's try Bn equals alpha n squared plus beta n. And if you think about it, if I just put in something that's linear, it's going to cancel on both sides. So I have to try something at least quadratic and bump it up. And so now if I try this, I'll get Bn plus 1 plus alpha n plus 1 squared plus beta n plus 1 equals Bn plus alpha n squared plus beta n plus 1. So I need alpha n squared to equal alpha n squared. I'm just going to match the terms in n. Then the next term, I'm going to have a 2 alpha n plus beta n. And on this side, I'll get beta n plus n. And then the constant term would be alpha squared plus beta equals 1. So from the first equation, alpha n squared equals alpha n squared. Do we get anything from this? No. For the next one, we get 2 alpha n plus beta n equals beta n plus n. Oh, that's good. What does that tell us? So what do we deduce from this? Alpha is 1/2. And for the last one, well, now that we know alpha equals 1/2, we have, oh, it's not alpha squared. I made that mistake. It's not alpha squared. What is it? It's just alpha, right? Because we're doing alpha times n plus 1 squared. So we just get alpha plus beta equals 1. Therefore, 1/2 plus beta equals 1. So beta equals 1/2. So we try an equals bn plus alpha was 1/2 n squared plus 1/2 n. We know bn equals b0, so let's just write b0 over there. what does we need just one value of A. What does A1 equal? 1. Therefore, what will be 0 equal? 0. And so now we get AN is 1/2 n squared plus 1/2 n, and in a remarkable bit of factorization, it's 1/2 n times n plus 1. And so from this, we are able to get the explicit formula for AN just by guessing. Do you think you can use this to get a formula for the sum of squares? Yeah, sum of cubes. Yeah. So here's my question to you. Can you use this to prove that the sum of squares, cubes, and whatever has to be a polynomial of degree 1 higher than whatever power you have, with leading coefficient 1 over the degree? So for example, if we have 1 to the k plus 2 to the k plus dot 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 plus n to the k, this is going to be some polynomial in n, and it's going to start off with n to the k plus 1 over k plus 1 plus dot dot dot. And what's the constant term going to be? If you want, I can write it like this: 0 to the k plus 1 to the k. What's the constant term have to be? Has to be 0, because when I take n equals 0, I get a sum of 0. So here's my question: can you prove that the sum of the kth powers of integers has to be a polynomial of degree k plus 1 with leading coefficient 1 over k plus 1? And so if people are interested, we can make this an extra credit question. I'm not sure if this has ever been written up in the literature as to a nice way to know that it has to be a polynomial. There are other tricks you can try, and again, I'm never sure what's been done before. What's k plus 1 squared minus k squared? This is just 2k plus 1. So if I do a sum, k goes from 0 to, say, n minus 1 of k plus 1 squared minus k squared. This is going to be a sum. K goes from 0 to n minus 1 of 2k plus 1. All right, what can you tell me about this sum on the left? It telescopes, and what do you get?
K squared minus 0.
Okay, not k squared, though. Not k plus 1 squared. I'm sorry, n squared, because k is going from 0 to, yeah. So you get n squared, and over here, you'll now get a sum. K goes from 0 to n minus 1, pull out the 2 of k, plus a sum, k goes from 0 to n minus 1 of 1. So if we know that this is a polynomial in n, we now get that this is a polynomial in n with degree 1 higher, and we would get to divide by 2. So can you use this to then inductively go up and prove that if I give you a polynomial of degree k, it's going to be a polynomial of degree k plus 1 divided by k plus 1 as the leading term with a constant term 0. This is another way to try to prove it. And again, I'm not sure if stuff like this has ever been written up in the literature. If people are interested, this could be a fun thing to write up. It's nice to just see how far you can push these elementary arguments. What I will end with is just for the last minute is let's try to do Stirling's formula. And so rather than proving it, which we'll do later, let's break things up in half. And so again, I'll assume n is even. And so when I look at my product, I have all the terms up to n over 2 and all the terms from n over 2 onward. Can you give me an upper bound for this product? What's an upper bound for that product? Why n squared over 2? Good, we have n over 2 terms times n. And for this, for the first part over here, what's an upper bound for that? Yes. Yes. This should be, thank you, this should be n to the n over 2, because it's a product. And for this one, we have n over 2 to the n over 2. So n factorial will be less than equal to n halves to the n over 2 times n to the n over 2, which is n to the n. And then you would have a 1/2 to the n over 2, right? So this is going to be n to the n over square root of 2 to the n. N to the n over square root of 2 to the n. Compare this to n to the n over e to the n. And then what you can do is you can keep doing this dyadic decomposition. And as a nice exercise, you can actually see that it's getting closer and closer and closer to e to the n. Can you get the square root of 2 pi? So I don't know if that's ever been done. I will put some notes about that on this as another nice extra credit problem. All right, have a good rest of the day. We will continue on Wednesday.